Hello, my name is Jackie and I'll be talking about the different cooling methods employed in turbofan engines. So first off, let's look into how a turbofan works. This picture right here is a typical turbojet. I think we're all to some degree familiar to how that works. We have the inlet, compressor, combustion, turbine, and nozzle. Turbojets use all the air intake for combustion, which means all the power produced by the gas turbine is used by the compressor. Thus, the output of the turbojet lies in the energy of the exhaust gases as opposed to the shaft power. However, with this configuration, there is an inherent inefficiency regarding fuel consumption. In order to solve this problem, we introduce something called bypass, which you can see is the light pink area, such that the turbine powers not only the compressor, but a large ducted fan. This introduces a new parameter known as bypass ratio, which is the ratio of the mass flow rate of the air that goes into the ducted portion and the air that goes to the core to be combusted. There are a couple of other important design parameters in a turbofan, like turbine inlet temperature and fan pressure ratio. So what are some of the reasons we want to cool our turbofans? We know that a gas turbine engine follows the Brayton cycle, and thus one of the most powerful ways of improving the efficiency is increasing turbine entry temperature. Modern turbine blades consist of a nickel superalloy with a melting point of 2500 degrees Fahrenheit. However, modern turbine entry temperatures can reach 2700 degrees Fahrenheit. Due to material limitations, modern-day power plants employ a variety of cooling methods to ensure that the turbine does not melt during operation. A rule of thumb is that blade life is halved for a specific blade material and cooling technology for each 10 degrees Celsius rise in temperature of the metal. The cooling methods used today can be loosely categorized into internal convective cooling and external cooling. However, there are a lot of different methods that won't be covered, and this is by no means a comprehensive list. For this presentation, we'll go over some of these methods and how they work, and we'll look into some newer methods of cooling. So internal convective cooling is the method of directing coolant via the available pressure gradients into the necessary components and thereby achieving a reasonably distributed thermal condition. About 20% of the compressed air prior is bled for cooling purposes. The pressure at the first stage of the turbine is less than the compressor exit, and thus this pressure difference drives the air into the internal serpentine cooling passages. Turbulators or rib rougheners are cast on the walls of the internal passages and cool the mid-chord region of the blade, and they introduce a turbulent mixing of the air, which increases heat transfer. Their geometries can vary with angles with respect to the flow, shapes, and configuration, as we can see on this slide. The picture on the left models the flow structure for different rib spacing ratios, and on the right you can see how the angle affects the Nusselt number, or the ratio of convective to conductive heat transfer at a boundary in a fluid. The trailing edge poses many manufacturing constraints which prevents turbulators in that area. Pin fins are typically used just for this purpose. The pins form an array along the trailing edge of the blade, and as the coolant flows past the pin, the flow separates and wakes are shed downstream of the pin. These wakes form vortices which enhance the turbulent mixing of the flow and thereby enhancing the heat transfer, as you can see with the picture on the right. For external methods, there are two I'll be talking about, which are the primary methods in modern engines: impingement jets and film cooling. The jet impingement technique is a cooling technique where the coolant impinges on the hot surface, creating stagnation point flow and a consequent wall jet. Jet impingement channels consist of holes machined on insert plates inside the hollow blades throughout the span, which is illustrated on the picture to the right. Film cooling is one of the major technologies that has allowed turbine entry temperatures to be as high as they are today. It is the bleeding of internal component cooling air through the external walls to form a protective layer of cooling between the hot gases and the component external surfaces. Much of the design of film cooling is concerned with hole entry, hole shaping, orientation, spacing, momentum flux ratio, effects of mainstream turbulence intensity, external surface curvature, and external surface roughness. As you can see on the picture to the left, the experiment illustrates how different geometries generate different film properties. On the right, you can observe the holes that allow the cool air out and form the film. With the demand for more thrust increasing and a push for more efficient engines, simply passing coolant air through the airfoils does not provide adequate cooling. Therefore, it is necessary to implement techniques that will further enhance the heat transfer from the airfoil walls. As you can see in this model of a turbine blade, numerous internal and external cooling methods are required to allow it to operate in temperatures way above its melting point. New technologies in the field of turbine cooling are driven by the need to operate the turbine at higher temperatures. Dimple cooling is a desirable alternative to pins due to a relatively low pressure loss penalty. Swirl impingement is a combination of impingement technologies and swirling techniques. Studies show that screw-shaped swirl cooling can significantly improve the heat transfer coefficient over a smooth channel, and this improvement is not significantly dependent on the temperature ratio and rotational forces. And heat pipes transfer heat from high temperature to the low temperature regions. They are currently employed in the stators of the turbine, but research is ongoing for implementing them on turbine blades. So those are the cooling methods employed in turbofans. Thank you for listening.